Welcome back, everyone. Today, we are tackling a concept that is literally the absolute backbone of green hardware. I mean, if you've ever wondered how your modern devices manage to balance incredible lightning-fast performance with a battery life that actually lasts all day, well, it all comes down to a very specific set of mechanisms that we are about to unpack. Okay, let's dive into this.
We've got a fantastic roadmap for this explainer. First up, we'll look at the always-on problem of early computers. Second, the golden equation of power consumption. Third, the actual DVFS architecture. And finally, we'll see DVFS in action.
All right, starting with Section 1, the always-on problem, or basically the major flaw of early computing.
To truly appreciate where computing is today, we really have to look back at a critical flaw. Back in the day, a CPU was, well, pretty one-dimensional. It ran at its absolute maximum clock speed, 100% of the time, burning max power regardless of what it was actually doing. So the ultimate solution to that massive idle hour waste? It lies in these four letters, DVFS. Dynamic voltage and frequency scaling. It's a power management technique where the operating system constantly monitors the real-time computational load and then dynamically adjusts both the voltage and the frequency of the CPU on the fly. It is quite literally the core technology preventing your laptop from melting right through your desk.
And this brilliantly illustrates why DVFS is just so essential. Think about two drastically different workloads. On one hand, you have a massive 3D simulation pushing millions of polygons, right? And on the other, you're just typing a simple sentence into a Microsoft Word document. Drawing 100% maximum voltage for both of these tasks is complete insanity.
To put it in a universally understood perspective, running a CPU at maximum power while you're just word processing is like keeping your car's accelerator mashed to the floor at 10,000 RPM while you are parked at a red light. It destroys the engine, it wastes a massive amount of fuel, and it generates a completely unmanageable amount of heat.
Which brings us to Section 2, the golden equation. This is the secret sauce of green computing.
Now, what's really interesting here is how we fix this mathematically. If you're taking a computer science exam, this exact concept is what examiners actively hunt for in your answer booklets. This massive formula is essentially the cheat code for power savings. It's the equation for dynamic power dissipation in CMOS circuits. P equals C times V squared times F. If you're trying to understand power consumption at the bare silicon level, this right here is your treasure map.
Let's rapidly define what each of these variables actually represents. P is the dynamic power consumed by the processor, measured in watts. C is the load capacitance. Now, pay close attention to C, because this is a physical property of the silicon itself. Once that chip leaves the TSMC fabrication plant, this number is locked. Hardware engineers cannot change it. Then we have F, which is the clock frequency in hertz, and V for the supply voltage. Since C is locked, we only have frequency and voltage left to manipulate if we actually want to save power. Just look at the mathematical relationship here. Frequency scaling is strictly linear. If you drop the clock speed by 50%, the power drops by exactly 50%. That's helpful, sure, but look at voltage scaling. Voltage is squared in our golden equation. It has a quadratic relationship with power consumption. So dropping the frequency is great, but dropping the voltage, that yields exponential energy savings. That is the true secret sauce that saves the planet.
Let's do some quick math to prove it. Say an operating system dynamically reduces the CPU voltage by a mere 20%. The voltage becomes 0.8. Since voltage is squared, 0.8 squared is 0.64. Meaning a tiny 20% drop in voltage mathematically results in a massive 36% drop in total dynamic power consumption. It's incredible.
Moving on to Section 3, the DVFS architecture. This is where hardware truly meets software.
So, the math is undeniably brilliant on paper. But how does this equation actually come to life inside your laptop or, say, in a massive cloud data center? It really begs the question. How does the physical silicon actually know when to drop the voltage? CPUs are incredibly fast, sure, but they're completely blind. A processor can't make these decisions alone because it has absolutely no idea what applications you are actually running. It needs a brain to tell it what to do.
Let's move through this and see how it builds into a seamless relay race between software and hardware. Step 1. The operating system monitors your workload. It sees, hey, they're just reading a PDF. Step 2, the OS governor, which is an algorithm in the kernel, decides max performance just isn't needed. Step 3, it requests a lower power state using ACP/IP states. Step 4. The physical hardware's voltage regulator module, or VRM, receives this command. And finally, Step 5. The hardware physically executes the drop in voltage and frequency. The baton passes perfectly from the OS brain right down to the physical silicon.
In the real world, tech giants actually have their own proprietary names for this whole architecture. Intel calls their implementation Speed Step or Speed Shift, AMD refers to theirs as Cool and Quiet or Precision Boosts, and hey, if you were watching this explainer on a smartphone right now, your ARM processor is executing these exact 5 steps hundreds of times a second just to prevent your battery from completely draining by midday.
All right, Section 4, DVFS in action. Let's look at the temporal waveform.
To completely cement your understanding here, we need to visualize how this dynamic scaling actually behaves over time in a real-world scenario. At time 1, you launch a heavy 3D game. The OS instantly requests maximum power, spiking the voltage to 1.3 volts and frequency to 4.5 gigahertz. Then, at time 2, you close the game and the heavy workload abruptly crashes. Now, without DVFS, your computer would just keep burning that 1.3 volts, wasting all that energy as pure heat. But with DVFS, at time 3, when you're back to just reading a PDF, the system dynamically steps down, safely dropping the voltage to 0.7 volts. The power being drawn perfectly tracks the actual workload.
But you know, that introduces a pretty fascinating narrative twist. If dropping the voltage saves exponential amounts of power, why don't we just drop it all the way to 0 when the computer is idle? Why not run the CPU at 0.1 volts and save infinite power?
So the crucial point here is understanding the absolute physical limitations of electricity. It all comes down to something called the threshold voltage. Simply put, this is the absolute minimum electrical pressure required for a physical transistor to actually switch states between a 1 and a 0.
If you drop the supply voltage below this physical threshold boundary, well, the transistors just simply fail to flip. The logic gates start outputting complete garbage data, and your system crashes instantly. Actually, this is exactly what happens to aggressive overclockers who try to undervolt their CPUs a little too far. They are immediately met with the infamous blue screen of death. The sheer brilliance of DVFS is that its algorithms are designed to safely navigate right above this critical crash line.
Okay, let's summarize this masterclass. We've seen exactly how DVFS adjusts power in real time through this incredible hardware-software partnership. We've unlocked the golden equation, proving that a drop in voltage yields massive power savings. We tracked how OS governors trigger ACPIP states, allowing the actual voltage to perfectly hug the workload curve, saving both your battery life and, quite frankly, the planet. Mastering these specific concepts proves a really deep understanding of how software can physically dictate electrical draw.
But before we wrap up today, I want to leave you with a provocative thought. We've pretty much completely solved computational efficiency for the CPU. But what about the rest of the data center? What about the massive towering arrays of spinning hard drives storing petabytes of cloud data? Are they just spinning 24/7, burning power even when no one is accessing them? How do SSDs fundamentally change the power per terabyte metric compared to traditional HDDs? That's a massive challenge involving MAID, or massive array of idle disks architectures, and it's a puzzle that is literally reshaping the modern internet. Keep that in mind next time you upload a file to the cloud. Thanks for learning with me today, and I'll catch you on the next explainer.